Hi there. Welcome back. So in this video, we will be diving into the intricacies of IDA. For those who do not, IDA is one of the few tools that reverse engineers use that could help them reverse engineer programs. So this video will be as a proof of concept on how to reverse engineer simple C++ programs, and to do that we will be using IDA. So the first step to do, guys, is to install IDA. You could use the um, you could use the free version that is in the internet. So it is available for everyone, and if you want some more features, you could buy the pro version. So to practice the usage of IDA, guys, we will be using a simple C++ program from RootMe. So you can just go into the cracking category and then download this binary. So it's a C++ program that have zero protection on it. So I think it's a great sample to learn on. So we will be practicing on this binary. And I suppose RootMe does not have any problem with solving the easiest problem of them on the internet, because they have some kind of regulations on solving their binaries online. But I suppose they won't be having a problem um, with this binary specifically, because it's solved by almost everyone. So yeah, so let's download the binary. So let's copy the link. Where else do we have? So we download that binary. So the first thing, guys, we do always is to check the format of the file. So we do file challenge 25 binary. So it is an old 32-bit that is little Indian with a dynamically linked libraries. This is the interpreter of the this is the path of the interpreter, and it is for Linux, and this is the hash of the binary, and it's not script, which means that all the symbols and the function names are available for us. So yeah, so let's check strings if there is before checking strings, let's try to run the binary and see how it is behaving. Um, it is asking for a password, so it's saying that the usage of this binary is by giving the binary name and the password. So let's, for example, give it ironbyte hi. So password is incorrect, so I suppose there is some kind of password that we have to give the program um, in order to successfully validate this challenge. So let's try to run strings now to see if there's any kind of string that we know. Challenge binary. So what do we have? Yeah, it's Sykes, libc. So this is the libc that we'll be using. This is password. Okay, these are the messages that will be printed when we give the right password, I suppose. This is the password incorrect. This is the compiler, which is GCC. So it's a C code or a C++ code, I'm sorry. Okay. So those are the sections. So since it's not strict, we have all the names. Okay. Let's fire up IDA, guys, and let's try to drop that file into IDA. Explorer. Um, hmm, okay, let's throw that into IDA. So guys, we will be using the default settings that are given by IDA. We won't be changing anything, so the processor is already used. We will be using the processor type that was given to us by IDA. So he is trying to identify the processor used. So when you switch the processor type, you actually switch the assembly that will be generated to you by IDA, and we will be doing that. So do you want to change the processor type to that? Let's say to no. And then we actually have this. So in the left, guys, we see the function names. So this is the function names that IDA will generate for you, that gives you an idea of how the functions, what are the functions, I'm sorry, used in this binary. So we have main, we have and other bunch of other functions used by C++, which are string, and compare, and etc. So this is the constructor that we'll be talking about. So the calling convention used is the CDECL, okay? So argument counter and the argument vector and the EMVP, okay? So what do we have now? So let's try to first do some basic static analysis on how we can link, for example, the fact that he is giving us the usage when we don't give a password, and when we give a password, he's going to do some other block. So and the first thing that you could notice once you open up IDA is that it is going to be giving you a bunch of blocks, and each block is actually doing some code. So this is actually called flow if of e program, or e graph flow of the program. Now, what is really interesting, guys, is that IDA can help you also do something decompiling. You can decompile using F5, but actually, when we try to decompile this specific binary, I cannot do that because IDA is failing to do that those analysis. I don't have any idea why IDA is doing that, but it's okay since this is a great opportunity for us to apply the assembly that we have learned in the previous videos. And we will be doing that for sure, just using dynamic analysis along the way too. So we will be using GDB in case we need it. So let's try. Let's try now to understand um, the entry point of the program, or find out the entry point. So now when you fire up IDA, IDA gets you directly into the main. So those actually are a bunch of variables, and those actually a bunch of arguments. So whenever you find when IDA names for you, for example, variable 16 or variable 15 or variable 14 or whatever it is, it's actually the 14 is the offset from the EBP. So actually those are variables allocated on the stack, and those are the arguments that was passed to the main. So as we have talked in the previous videos, argument C and argument vector and all the kind of arguments are actually generated before running the program, and are all of them actually are calculated before running the program itself. So yeah. So the first thing that the program is doing, he is doing the usual stuff. So he is doing the function prolog. So as we can see, he is loading from the ESP plus 4 um, uh, that address to the ECX, and then he is doing something called stack alignment, trying to align the ESP with this address, and then he is pushing that value in the ECX4 into the stack, and he's pushing the old EBP, moving the EBP with the ESP, and then pushing or saving EBX and ECX, and then he's allocating 20 bytes on the stack. Now he is also moving what's in the ECX into the EBX, and then he is moving one. I'm sorry, he's trying to compare one with what's in that address. So if we go back a little, EBX contains what's in the ECX, and what's in the ECX is actually what's in the ESP, um, what's in the ESP plus 4. Now, what's really interesting is that that is actually supposed to be the argument count. Why? Because actually when he is trying to compare what's in the EBX with one, he is going to be jumping either to the left or either to the right. So if we try to, for example, try to see if he is jumping to the left, which is the condition is false. So when the comparison failed, so when the EBX is different to one, or when the value pointed to by the EBX is different to 1, so he is going to go to the block where he is gonna be moving some stuff into the stack again, and one of them is actually usage. And as we can see, this is the usage string, and then he is moving on the offset of the cout, which is a function used in C++ to print something in the output stream. And then he is calling the operator, as you can see, inferior. And this operator is used, for example, to redirect something to the output stream. We usually do that, for example, um, let me just open up VS Code. Okay, so we usually do that, for example, when, for example, doing like iOS stream, IO stream, we have the main function. This is the return 0, and you usually actually use it like that. So we call the standard output and we call the hello world and the cout function. So now what's really interesting when we see the code, it is actually doing what we call just trying to move what's in the EBX plus 4 into the EIX, and then it's trying to get the value pointed by EIX into EBX, and then it is moving the string usage into the ESP plus 4, which means this is like this instruction is like saying push the string usage into the stack, but he is doing it like manually or something like that. So he is now moving the usage into the ESP plus 4, and then he is moving the offset of the cout into the ESP, which is the top of the stack. And now he is calling the operator, which is the double inferior. So if we try to mimic or see what's in the code, we see that this is the cout and this is the string usage. So, and this is like a function that he is calling on these two parameters, which are the cout and the hello world. And then he is moving what's in the EBX that we have loaded later on into the ESP plus 4, and then he is again calling what's in the EIX and putting that um, into the ESP. So if we just try to look back a little into the program, we see that there is something which is the CH25 this is actually, as we have talked in the video of how executables are working, we always put the first argument as the name of the binary itself. So now he is loading again the name of the binary into the operator, and then he is printing that, and then he is doing the same with the password and the same with the other instructions. So for now, we don't have to reverse engineer too much about what is happening in the usage, but as long as the conversion is 1, it means that the argument count is 1, then we will be going into this block, which is this one. So for example, when you do um, you give him a random password, he's gonna be printing to you password incorrect. So I suppose there is some kind of logic in this place to understand. So for now, if we see a lot, then we see some kind of comparison that happens when he do a lot of magic, and then he is doing some comparison. So the comparison is saying that, for example, if the AL, I don't know how this AL is generated, we will be trying to see. So if we are testing the AL, if it is a 1, so if it is a 1, then it's not a 1. I'm sorry. GZ means if it's 0, so if it is not a 1, then he's going to be given us the block of the password incorrect. Otherwise, he will be given us the block of congratulations, we can validate with this password. So how can we now understand this? We will be using some static analysis by trying to learn line by line how this code is generated, or how this code is working specifically. And again, we will be doing the same stuff that we have tried to do in the previous video when we tried to use GDB, but this time we will be using IDA, but we will be reversing the code line by line. Okay, so we start with the first one. So let me just try to copy this code and get it into let me see. Let me get all this code into VS Code and let's analyze it in VS Code. Okay. Um, what else do we have? I think we can do some comments in here. Yeah, we can do comments. Yeah, we can use comments on IDA itself. We don't have to copy it into VS Code. Okay, so what this line will be doing is that it will be, let's start, for example, hi. Let's do test the comments section if it is working or not. Yeah, it's working. Perfect. Um, okay. Okay. So let's start with the first line. So he is loading some address from the stack. So this is a variable that was allocated. So he's moving that value or the address of that offset on the stack into the EIX, and then he is moving what's that address into the stack again, and he is calling the allocator. Now, what is interesting, guys, is that in C++, so since we are using allocators, allocators are always used with constructors. So whenever we have a constructor in C++, for example, for any kind of class, we use allocators. So let's move on and try to understand more what's happening. So he is moving now. So he is calling the allocator on that address. So he is trying to allocate um, he is trying to create an allocator by calling the constructor of the allocator. So this is called a constructor, guys. So this is specifically the constructor. Um, and now he is moving what's in the variable 15 into the AIX, and then he's putting that at the offset of the ESP plus 8, and then he is moving some other offset of some bytes, which are 18, D6, etc. So he is moving those bytes into the ESP plus 4. So this is kind of the second argument. And he is loading again another address of a local variable, which is the variable C, into EIX. And then he is moving that into the top of the stack, and he's again calling now another constructor, which is now the constructor of his string. So I suppose now in this position he is using the constructor of a string and using the allocator to create a string um, that will be saved into the variable C. In another word, if we look at this in a much more high level code, it could be something like that. So it could be like trying to create an allocator, allocator, which is, for example, in our case, will be an allocator for char, since we are trying to allocate something for the characters. We'll be trying to see the code also. I suppose I have saved it in using the wrong name. Was supposed to be code. Okay, I suppose it's code. Yeah, so now we will be trying to create a string. Let's call it street. That will be equals to, for example, hello world, and we will be creating a string. So we will be calling the class string, and let's call it tree um, with the type of string. So if we call the constructor, we pass on the allocator, which is allocate, and then we pass on the string. So if we look back, so mm, okay, um, let's ignore that for now. So we have to include also um, the string the string library. What else do we have? So we'll be outing that. So um, let's try to compile this code. Um, so we will be compiling that using G++, error, okay. Okay, since we are having some kind of problem, let me see. Is it that we will be having that as a constant? I forgot how to do this exactly. I need to check out the function, I think. Let's just see either if I'm making this wrong. This is an allocator. I forgot the constructor, I'm sorry. I suppose now there's no problem with that. There's still a problem. Uh, okay. Maybe the string is first, I don't know. I'm just trying to use my mind because it's been a long time since I have seen it. Okay. We don't have to co-use this, I think, now. Um, I suppose okay. Now it's working. I don't know what I've changed. Ah, yes, the order. I'm sorry. The order of the constructors. Um, this should be, I think, a constant to a string, and this should be the allocator. Why am I just didn't see that? Yeah, this is one. Yeah, the allocator is the second one. Yeah, sorry for that. Yeah. So as you can see now, if we try to run the code, so it's given us hello world. This is how you actually can allocate a string in C++ using the string constructor. So as you can see, guys, we have used the string constructor to do that. So another way to do that actually should be using the operator also. For example, we could use the operator directly, like for example, like that. This is just another way of doing the same thing. But this in this one we have used an allocator, and in this one we have used um, just the operator equal to do that, to assign the hello world into the variable ss. So yes, so basically now if we go back into IDA, we have seen that he passed down the allocator and the string to be passed down, and this is the result of the constructor, or um, the new created string. So in this case, after just calling this one, we will be seeing, like, at this point we will be seeing variable c will be equals. Let's try to rename variable c into another name, for example another meaningful name. For example, let's call it street. So this is 3, and this is will be given as variable or street equals to some bytes or some string. Let's say some string, yeah. So just after calling that, so 3 will be equals to some string. So what do we have now? So we have variable 16. So we can also rename that into allocator 1, allocator um allocator 1. So this is like a better version of how we can reverse the code. So guys, the first thing that you have always to do is rename variables whenever you have like noticed something in the code. So this is an allocator, and this is a string, and the unencrypted one we can also rename it. So we call it, for example, string 1. Okay, so this will be doing like string equals to some string. We can just call it, for example, um, we can try to change that into, for example, string 1 directly. Yeah. So what do we have now? So we have variable 16, which be always which will be also passed into an allocator. So this is another allocator. So let's call it allocator 2. This is the allocator too. It will be used on, so he is passing that with as the third argument, then the second argument, and then the top of the stack will be another string. So let's call this string 2. And let's see this string. So I think it's a bigger string than the other one. So let's just call it string 2. So yeah, so he is using another allocator. So with this string 2, and this is the string 2. Okay, so he is calling this one. So let's try to so he is using the constructor of the second string. Just to make, for example, string 2. Let's call it 3. We have gave it the same name. Let's just try and just call it, for example, 3 2. This is a better one. Okay, so 3 2 equals to string 2. Let's see. So okay, just after doing this call now, 3 2 equals to string 2. Okay, so now we have loaded the effective address of variable 14 into the EIX, and then we are loading the string 1 into EDX, and then we are passing them to the stack, in the stack, I'm sorry. So 3 is the third argument since we have a plus 8, plus 4 for the argument 2, which is the string 2, and then we are moving what's in the EIX, which is another string, I suppose, or another variable for now, because we don't know yet. And he is calling some kind of function called ploof that takes two strings. So that makes sense actually. So this is why he used this is why, I'm sorry, he constructed the two strings using the constructor of the class of string, because he is passing two strings. Okay, this is logically true. Now let's just try to, for example, skip for now what is happening in the proof, because the proof has some kind of logic inside of it. Now he is subtracting from the ESP4, and then he is loading the effective address of the string into EIX, and then he is passing that um into he is pushing that, or let's just say he's moving that to the top of the stack, and then he is calling the deconstructor, I suppose. Since we have this symbol, we should understand that the deconstructors in C++ are written that way. So after just um, creating this string, he is calling the deconstructor of that string. So that means he is trying to delete this string from memory, from the memory. What else do we have? So he is calling also the allocator, and he is calling the deconstructor of the allocator, another deconstructor, and another deconstructor. So I suppose he is getting rid of the allocator one and the string, um, yeah, the string one that we have generated, and the allocator two, and the string two, and then um, he is moving on what's in the EBX plus 4 to the EIX, and then he is adding a 4. Now, what is really interesting that we have said, we have seen that value before. Now, what's in the EBX? If we go back a little, what's in the EBX? So the EBX contains what's in the ECX. And if you remember that, we have said that that the EBX contains the value of the argument count plus 4. So if we add a 4, actually, we actually got the second argument, which is the actual password. What does that mean? So actually, the EBX plus 4 contains, let's say for now, when you do, for example, if we go back to the binary, it actually contains this this string, which is the challenge 25 dot binary. But when he adds e4, he actually gets to the other one. So for example, if we pass some kind of string, when we add a 4 to the EBX, we get this one, and then as you can see, he is trying to dereference that, and then he is moving that value into the EIX, and then he is passing that into the stack, and then he is giving the variable 14 as a second argument, and then he is calling the function or the operator double equals. So double equals is used to check if two strings are equal or not in C++. So by trying to do some static analysis from the code, we have just understood that he is comparing. It's like he is saying like that, for example. So that code means that, for example, the password if the password is equals to the, let's say for now the variable 14 contains, as we can see, since it is called um, since it is passed, I'm sorry, in the ploof, I suppose ploof will be generating some string. So let's just call it generated string. This is generated string. So this is some generated string. So if the password is equals to the generated string, um, then we will be doing some tests now. If they are equal, we will be doing um the the password. It means, I'm sorry, I always got caught by the GZ or the GZ. I'm sorry. So the GZ will be doing like, if it is not true, it is going to be password incorrect, and if it is true, it will be giving you the congratulation message. So it will be printing congrats, congrats. Otherwise, it will be giving you fail message. So this is basically what is happening um, at this block of code, or this block of instructions. Now, what is really interesting now, if we use GDB and try now some dynamic analysis instead of just, we can stop at this point and start just getting the idea of what is the value of the generated string at real time. Is it some string that is randomly generated each time we run the program, or is it some static one? Now, this is a good question to ask, but the first thing that we need to do is set a breakpoint at this call before we do the comparison, just to find out what is the generated string. And if it is, and if we, for example, um, have an idea about what is the generated string, then all what we have to do is just give him the password, because the password is compared with the generated string. Now that makes more sense, I think. Um, let's try to open up GDB and try to do some dynamic analysis on that. So GDB 25.bin, and as we can see, we have fired up GDB. Now, in this video, I have tried to switch up to another extension of GDB, just to change um, a little the extension, and at the same time, I wanted to show you PETA, which is another extension of GDB. Just as the previous video, we have used Jeff, and in this video, we'll be using PETA. So you can also do the same thing as Jeff. You can just check that out if you want. um, the installation is available. It's pretty much easier than Jeff. All what you have to do is just copy these three lines into your terminal, and you will be having PETA set up into your computer. So yeah, now if we wanna, for example, disassemble, let's see, for example, the available functions. So info functions, so there are a bunch of functions that are available. We want the main, so if we try to disassemble main, we see all of that. Now, the line that was interesting is that, let's see what we have. Um, so yeah, we wanted to see, so if you click on your space on the keyboard, you could get, or you could switch from um, graph view, or the flow view, or the flow of the graph, I'm sorry, to the text view. So yeah, all what you have to do is click on your space in the keyboard. So what else? So we wanted to see this specific line. Yeah, so this is the address of the call. I will be copying the address, which is in the text segment or the text section, and then we will be trying to set a breakpoint at this address. Another interesting thing is that in this binary there is no pi, which means that the the address space is not randomized, which means that each time the address will be the same. So yeah, we will be trying to set a breakpoint at this address. So we have set a breakpoint at that address, and now let's try to run. So if we run, um, it is saying warning. Okay, I suppose because of the usage, I think. Yeah, okay, the usage, yeah. Since the breakpoint actually is in the block um, that contains the password, we should be specifying a password in order to hit the breakpoint. So we run, for example, with iron byte. Okay, since we are in now, I think we hit the breakpoint, so we are um, at this instruction. Now, all what we have to do, guys, is just check out the values that were passed in the stack, and because the generated stack, for example, is in the top of the stack, so if we go to the stack, we see that the value at the top of the stack is the generated string. So I think at this point we have successfully um, find out what is the generated string. Now, the question that is really interesting, if we run again, is the string is gonna be regenerated or randomized? This is the question that we have to answer. So, for example, if we run again with set, it is the same. If we try again, it is the same. So this is a static string that is generated. Um, and I suppose he is comparing the password with that string. So if we give him, for example, this password, if we go back and try again with that string, we actually bypass the challenge and we can validate with this one. Now he says, congratulations, you can validate with that password. So this is the password. Now at this point we have solved the challenge. As you can see, it's a pretty easy one. But what is interesting, we didn't yet reverse the function that is going to generate this string. Now, just by using dynamic analysis, we already solved the challenge. Now, if we switch back and do some static analysis on the proof function, now this is where the interesting part comes in. So let's try to reverse it on our own and try to understand how he is generating this string for us. So if we take a look, so he is passing some arguments. So he is passing the generated string in the top of the stack, and he is also passing on the string 1 and the string 2. The string 2 will be at the ESP plus 4, and the string 1 will be at the ESP plus 8. So that means that, for example, he is actually not passing two strings. He is actually, so IDA didn't all is not always gonna give you the right actually um, header of the function that he's trying to call. So sometimes you have to do that on your own. So proof is gonna be taking three functions, which are string s1 and string s2, um, string, let's do s2, and I suppose the result. So the result is actually the first one. Steady string, the result. Let's for now just call it the generated string. Yeah, generated string. I have actually, guys, based my um, based my thoughts just using the CEDCL calling convention, because the generated string is passed at the top of the stack, so that means that it is the um, I think I have wait a second, is it the right order of the parameters like that? Let me just look at this. Yeah, we have the ESP plus 8 and the ESP plus 4. Yeah, this is the order, yeah. So it's actually in the reverse order, yeah. So this is the order. So actually, so this is the one that he will be using. So this is the generated string. So this is the S1 and this is the S2. So I don't know how he is going to use them, but let's try to see the proof. So if we take a look at the proof, we can see that he is doing some usual stuff just by trying to save the registers and allocate in the stack some variables. We see some variables and the arguments. So as we can see, um, the argument 0 should be, we have said that it should be the generated string. Let's try to see. Let's try to see where he calls that, for example. Um, let's see. Yeah, I suppose this is the generated string because it is, as we have said, since it is the first one, then it's supposed to be the argument 0. So the argument 0 is the generated string. We need to rename whenever we have the chance. This is the rule. This is how we can, for example, do some great static analysis when trying to reverse engineer any kind of program. So this is the generated string. What else do we have? The S1. So the S1 is should be the string. It should be the string 2, I suppose. It should be the string 2. Um, I have missed with that. I've missed the order. I knew that I was having something there. So yeah, so this is the string 2, and this is the third one, which is string 1. Yeah. So this is string 2, and this is string 1. Okay. Just if we look back a little, we can just find out. For example, let's see. Now let's just move on and see what will be happening. So he is loading the effective address of variable 1D. He is moving that into the stack and calling the allocator. So this is an allocator. As we have seen, this is an allocator. Let's just call it allocator 3. Um, and then he is using that allocator to allocate another string. What is this string? So it is an empty string, I think. So let's just call it um, empty string for now. And then he is using the string passed in the parameter to give it, I think. So yeah, so this is what he's doing. So he is passing an unallocated string and he is assigning just some empty string to it. So yeah, this is what he is doing. So generated string is equals to something like that, exactly. Just by calling this function he is doing this. So what's next? So he is calling the deconstructor of the allocator 3 and he is moving 0 to the variable 1c. Now if we um, just some jump, we see that variable 1c, let's see how much this is called. So because there is some kind of loop in here. So the variable 1c, as we can see, there is an add and it's initialized with a 0. So that means that the variable 1c will be used as a counter. So let's just call it I, which is a trivial name for the counter. Um, then we will be going to jump into this location, and then we will be moving what's in the EBP or moving what's in the I into EIX, and then EIX will be passed on to the stack as an argument, and then he will be calling the string 2, and then he will be passing that to the stack and then calling the operator that. So this block is actually equivalent to just like saying, for example, SS, for example, of I. This is exactly what this block has done. This it's actually calling that. It's like trying to access the ith character to the ith character of the string. So yeah, so he is actually trying to do street street 2 of I. So this is basically what he is trying to do. So this is street 2 of I. Now he is moving with 0x actually, since we have move zx. What's in that EIX, which is actually, since EIX is the return of this call, EIX will be containing the ith character of the string too. So EIX, he's moving that byte or that character um, into AIX, but this time he is moving just one byte of that address into the AIX. So now he is moving the value. So I suppose this call is returning the address of that character. So he is referencing that address, and then he is moving the value of the character into AIX, but with a byte PDR. So since he is using the directive byte, I suppose we are getting just one byte of the AIX, and since we are moving, for example, a byte into a 32-bit value, we will be using the move ZX to just zero the other bits to um, just set them to zero. Yeah, and then we will testing if it is a one, for example. Then we will be doing set nz. So what does the set nz do? We can just Google that if we want. So set nz, what does this do? So the set nz sets the byte in the operand to 1 if the 0 flag is clear. Otherwise, sets the operand to 0. Okay. So this is basically is kind of checking if it is 0, then we will be setting it to 1. We will be setting it to 0. I'm sorry. Otherwise, we'll be setting it to 1. So then there is another test. It will be testing if the and then the result would should be actually redirected to AL, which is the destination as we have seen. So this is the destination of the instruction. Now, the AL, for example, in this case, since we are not zero, we didn't hit the 0 bytes. Um, we should be going into this block. Otherwise, we should be going to this block, which is exiting, going into the exit of this flag. And as you can see, when we try to exit, we move into the EIX, the address of the generated string that we have passed on. So that makes sense because if we go back into the main, we see that the generated string is passed on as in this function, which is the proof, and we are also trying to use the same string to compare with the password that will be given in the program. So that makes more sense. So the proof function is um, trying to modify the address or the variable, which is or the string generated string. So yeah, let's continue reversing the code. So what else do we have? So let's suppose we are now in this block. There will be some kind of loop, since we are having this arrow that will be going on if it is not equals to something. So this is the implementation of a simple loop in assembly. So we are moving the I into EIX now, and we are again passing that value to the stack, and then we are moving the address of the string 2 into EIX, and then we are moving that into the stack, and we are calling another function, which is the operator, as we have seen. So this is basically just doing string 2 of I. I suppose, yeah, this is string 2 of I. Yeah, it's the same block as the other one. As you can see, it's the same block. And then we are actually moving that value, which is the result of this call into the ECI, and then we are moving the I into the EBX, and then we are moving the string 1 into EIX, and then we are passing the offset of the string 1 into ESP, but this time without moving the I, and we are calling the length of the string. So this is basically will be given us the length of string 1. So the result of this function should be in the AIX. So the value now of the AIX should be containing the length of the string 1. So if we do that, so AIX contains the length of string 1. Okay, so the AIX containing the length of the string 1, and I suppose we can also just complete that and give ADI the same value of the EIX since the EIX is moved into the EDI. So the EDI now contains the length of the string 1, and the EBX is containing the I. So the EIX now is containing what's in the EBX, which is the I. Um, Now we are moving into EDX 0, EDX equals to 0, and we are doing a division on EDI. So what this instruction is gonna do, it is going to divide what's in the EIX, um, what's in the EIX by EDI. So EDI actually is containing um, the length of the string 1, and EIX is containing I. So what this instruction is gonna do, so it's going to be doing EIX divided by EDI, um, and the rest actually of this should be in the EDX. So the EDX, so this will actually give you EIX equals to EIX divided by EDI, and EDX should be containing the EIX modulus EDI. Yeah. So this is exactly what will be happening just after doing this division. So as we can see, he is moving the rest of the division into ECX, and then he is moving what's in the ECX into EIX. So now EIX contains the rest of this division, which is um, I think just EIX modulus EDI, which means I modulus the length of this string 1. And then, so now if you do that, so ECX contains I modulus the length of the string 1. Now, I suppose we are having now the I modulus the length of the string 1 and the ECX, and now we are moving, I'm sorry, it's EIX. It's not ECX. Yeah, so it's in the EIX. So, and then we are moving that um, into the stack, and then we are calling the string 1 again. So we are moving the offset of that, and then we are passing that on the stack. So we are moving some kind of offset. So the offset now will be string 1 of this offset specifically. So yeah, so this is string 1 of I modulus length of string 1. So this is a pretty famous way on how to do, for example, on how to make a string stay in the boundary of a specific counter. So because if the counter is much more bigger than the length of the string 1, to make it stay in the range of, or in the boundary of the length of the string, all what we have to do is just use this instruction, which is I modulus the length of string of 1. So it's a pretty obvious way on how to implement just some limitations on the boundary to not access some inaccessible addresses when trying to travel a string. So what do we have now? So we have the EIX. So we are moving what's in the EIX into so we are moving that character actually into the EIX again with the same way. So since it's a character, we are getting a byte into the EIX, and then we are getting that byte into the EIX just by zeroing the other bits, and then we are XORing what's in the EIX with the ECI. So if we go back, the ECI contains the string of I. So if we go back, the ECI contains the string 2 of I. So now by doing this, he is actually doing like string, um, he is doing exactly, he is XORing what's in the EIX with what's in the ECI. So I suppose now EIXs will be containing string of I modulus length of string 1 of I modulus length of string 1 XORed with string 2. Yeah. string 2 of I. So actually he is just trying to XOR what's in the EIX. So he is XORing two characters of the strings. And then he is moving the result, which is the AL, into AIX again, just to make it as a byte. And then he is moving that into the ESP plus 4, and he is calling the he's again setting the he is moving the offset of the generated string into EIX, and then he is calling the ESP. So he is passing the new XORed character, and he is calling the generated string, and then he is calling the operator plus equal. So that means that the generated he's doing just the generated string is plus plus equals to the new character that we can just call it. For example, in our case, it's just this one. So the generated string is plus equals to that. So this is basically what is happening just after using this call. And then he is just adding one to the counter and so on. So this is what this loop is doing. Now if we try to mimic this code, we can just regenerate the same message as he is doing. We can just do a Python script to do that. So what do we have? So let's say, so the first thing that we need to do is to extract the two strings, which are the string one and string two. So to extract them, we can just get them from here. So this is the string one, and this is looks like a key. Um, and this one is the string two, and this is the message. So this is like a typical way, actually, guys, on how you can just encrypt, um, of how you can encrypt a message using a key. So let me just go back to the proof. Just if you just you look into this code, this is actually a pretty famous one. This is a simple XOR on how you can encrypt using the XOR operation if you remember that operation. So all what we need to do is just mimic the code, and we will be generating the same message as he is doing. So if we do, for example, message, so message will be a bunch of bytes, and key will be a message, will be also a bunch of bytes, and then we will be trying to go in the range of the length of the message and show the message of I modulus the key of I modulus the length of the key. Yeah. Now all what we have to do is get the key and the message. So the key is supposed to be the string 1, which is 18. So it is 0x18. So we have 0x d6. We have also 0x 15. 0x15, and we have 0x CA. We have 0xFA, I suppose, and 0x77. 0x77. Yeah. What about the message? So the message is kind of big, so I think I have parsed that. So I have parsed them. We don't already have to just copy them and parse the values that are in here, just to use all of them. So let's just go back. Yeah, and there is a value at the beginning, which is I suppose 0x15. Yeah. So let's try to run this code. Hey there. Okay. I think the length of the message is correct. Is the key correct? Let me see. For I in the message, um, uh, I and the length of the key. I suppose I have just used that. Let me just go back a little since I have tried to code it. I don't. Okay, never mind. Um, yeah. Let me just see what is the problem. I think we have reversed it. The right way. Let me see. Okay. Let's go back into IDA. Did we do it the right way? This is the message of I, and this is the length. Ah, I have, I have met the wrong one. Sorry. Okay. I think we are done now. Yeah. So this is basically how you do basic static analysis on C++ binaries. Don't forget, guys, that in this specific challenge, we have used a simple C++ since C++ binary, since as you can see, the function names are available for us, and it's a great experiment, I think, and let's say a great experiences for someone who don't know C++. I think now you should be able at least to understand what is happening behind the code, and yeah. So don't forget to follow me on Twitter, and if you have any kind of questions, you can ask in the comment sections. You can message me on Twitter too. And yeah, don't forget to subscribe and see ya in another video. Bye.